Hi, everyone. Thank you for attending today's webinar, Quick and Dirty versus Built to Last, Solar Layouts Done Right. I'm Kelly Pickerel, Editor-in-Chief of Solar Power World. And before we get started, I want to go over just a few items. You can download the slides and any additional resources for today's presentation in the resource window at the bottom of your screen. We will have a Q&A at the end of the webinar, so please submit any questions in the Ask Questions window. If we do not get to your question, our presenters may reach out to you afterwards. You can also expand your view of the slides by using the icon in the top right corner of the slide widget. All the boxes on your screen can be moved and resized to meet your preferences. And finally, if you are watching this on demand, you can still use all of these features, including sending questions to our presenters. If you experience any issues during today's webinar, try refreshing your browser tab. If you continue to have problems, try closing other apps and browser tabs that you may have open. You can click Help in the top menu for more troubleshooting steps, or you can ask our producer for help via the Ask Question widget. So let's get started with today's webinar on modeling utility-scale solar projects. I'd like to thank PVFARM for sponsoring this presentation. And today we will hear from Maksim Markevich, who is Head of Technology at PVFARM. So now I'll turn things over to him to get us started.
Thank you, Kelly. Appreciate the invitation and appreciate being here. Love those webinars. We have many questions, learn a lot from you guys, and also we hope that we also share some useful insights with you as well. So today we're going to talk about solar PV layouts, and those can be done right if we can define what right means. And we start with a definition, right? So we will start simple with what does solar layout means. So, and if we will go to the next basically slide, so what people typically think when they hear solar layout? They usually imagine something like that. So you have a kind of very enlarged view of layout with site context, arrays, blocks, rods, maybe some metrics from the left, right? So you basically have a snapshot of something that will be built. However, what actually a solar layout is, so what is behind, what's behind all of that, right? So we will talk a lot about it now. So first of all, I would say that solar layout is about multidisciplinary harmony. So performance modeling, civil engineering, electrical engineering, structural engineering, and procurement, cost estimation. Everything runs in sync, and everything runs in sync, seamlessly connected to generate energy. I would say layout is more like the most known representation of solar PV projects. There are other aspects of it, like performance modeling reports or single line diagrams, but layout is actually represents physically what's going to be built. And there are, and many people actually think that solar PV layouts, they're quite straightforward. Just arrays, rods, vast open areas. However, they are deceptively simple at first glance, yet remarkably complex upon close inspection. It's kind of a blend of juicy engineering, and that's why we kind of quite enjoy automating those. So again, everything runs in sync, seamlessly connected to generate energy. So let's talk now a little bit about those kind of hidden considerations. So everything starts with defining the buildable areas, right? So the transition from section to parcels to buildable area, this transition is shaped by code requirements, which dictate setbacks, easements, land use constraints. From there, contextual factors like topography, hydrology, infrastructure, they further influence the layout pattern, and they guide how the site is ultimately designed and optimized. So we usually say that the buildable area is a set of immovable boundaries. So this is the boundaries defined by land ownership and then by restrictions from the building codes, right? However, inside those buildable areas, there are plenty of other different areas where it is expensive to build layouts. And we call such boundaries like a movable boundary. So we'll talk about it later. Now let's jump to the next hidden consideration, which is civil engineering, right? When I showed you the PDF of that kind of layout, you don't actually see why the decision was made to actually not place trackers there or place trackers there, why the decision was made to use a certain kind of length of the trackers. or like a certain placement positioning, because, you know, gradient and hydrology probably were factored in. So as well as manufacturer tracker limitations, different manufacturer choice would result in entirely different layout. And that basically means that this is a high sensitivity aspect of it, right? So the next hidden, and I would say this is the most hidden, and piles are the most probably overlooked aspect of the solar layout design. So, and the reason for that is that people, you know, usually say, okay, we don't place trackers here because we have lots of gradient. But quite often it's not the dirt, like the dirt movements actually that defines expensive areas. Quite often piles define it. And that's why, you know, piles are the most overlooked aspect to it. So, you know, they affect even like a tracker drive lines, for example. There are certain trackers with a drive line that needs to be kind of aligned around the motor pile. It's kind of, you cannot see it in a 2D, but you always see it in a 3D, and the real world is 3D. That's why it's important to consider those things. So piles play a crucial role in defining the most expensive areas of the project. And that in such a way, they basically influence the array placement and overall design strategy. And quite obviously, there is quite important aspect, which is electrical considerations. The electrical considerations dictate a skid position, and basically because you want your blocks to be, I would say, as compact as possible to ensure the efficiency and cost optimization. Sometimes the skid position in an electrical kind of connection can define whether you're going to use trackers from that particular area or not. So now let's so basically, as you can see, there are so many additional layers to that simple layout. So if we'll go back to this beginning, right, you can see there's like a spatial layout, but there are plenty of things underneath of it. There are plenty of layers and plenty of discussions, conversations, trade-offs. And this is why kind of quite, I would say, romantical engineering, so to put all of that together and to get like a beautiful, well thought out layout. So now let's talk quickly about, and I will show you what kind of completed layout in PVFARM. It's around 325 megawatts project, and basically we'll try to show you all of those layers in a way so you can see the complexity behind simplicity. Okay, so yeah, we're doing a proper screen sharing of dev environment. Nothing could go wrong. So I hope you guys can see my screen, and we will start with this kind of same layout, right? So let's start from a kind of bird view, like a top view, exactly how we discussed it. So first of all, as you can see, layout contains a bunch of trackers, bunch of rods, bunch of blocks. So kind of everything seems connected. This layout has metrics, right? So each project has lots of metrics like cost, site area, equipment, you know, specific quantities. Especially it gets complicated when you use a bunch of different sub-areas. Like in this particular case, we had one sub-area on the left, one sub-area on the right. And so basically you can see how those metrics being kind of broken down by sub-area. And the next aspect of it is this layout. And this is like a real project, and it produces energy, right? So the energy is being calculated. This particular layout has multiple modules, multiple inverters, and then we got the energy production, annual yield, daily yield, performance ratio. And as you can see, the fact that those things connected, it helps us to actually calculate the energy. There are also, like from a kind of high level view, there is a cost report to it, right? We have OPEX, CAPEX, capital cost, which is breaking down into kind of sections of cost, like electrical, structural, civil, etc. And that's basically what kind of like a big metrics about layout in general, when we check it from the top view. Right now, before we go to the next kind of level of details, I want to show you another aspect, which is about cut and fill and piles. Right? If I'll switch this view, you will see that there were plenty of cut and fill in this particular project. I'll get closer so you can see the terrain following trackers. We can also check what it was before cut fill, especially in the areas where it was extensive. cut fill and then how it became after the cut fill. So this information is also kind of as a one of those kind of unseen layers of the layout. Right now, let's go to the next level, which is medium voltage circuits. This is basically the next biggest level. So let's hide the terrain and we will be focused on the medium voltage. So now, first of all, electrical, which is a very kind of common representation of medium voltage circuits, this can be seen on a single line diagram. So on this diagram, you can see how many blocks connected in the kind of medium voltage groups or medium voltage circuits when they needed to use sectionalizing cabinets or when they're connected in a straight line in a way. And right, so you can see like a very well-known electrical representation. However, there are like a plenty of things where you want to visualize those things spatially. For example, if we will go and pick the wire here, and we will basically colorize it by circuit index, we will be able to see different circuits in different colors. So you can see how many objects connected, and we can go even further. So we can go further in Model Explorer. You can see that substation connects everything together, and now you can see that the hierarchy starts playing the interesting game. So you can start seeing like those circuits, one after each other. And so then we can pick the one and we can get closer to this one and let's say isolate it, and we can get even more closer. And as we get even more closer, we start seeing the blocks connected, right? So let's say if you wanna, like one more time to understand how all of that connected together, you can follow on the Model Explorer, for example. And again, it's just an additional layer where, you know, if I go back to this circuit, you can see we have our first inverter, then some wire that connects it to the next transformer, then it goes another wire, and then another transformer. And so you can kind of follow the whole kind of connection line where it starts, how the cable size increases, etc., etc. Right? So now we're gonna go and isolate one particular block, like block number 49. You can see the DC capacity. We start seeing this as we get closer, we actually start seeing cables. So let's do the simple exercise. We're gonna hide annotations, and then we're gonna basically hide the trackers, and we will go to property analysis. We're gonna choose the low voltage wire, and let's say we're gonna colorize it by specification type. So we will start seeing extenders, trunk bus, feeders, right? If we're gonna go and choose the gauge specification, we'll colorize it number 10, 350 kc mil, 750 kc mil, and you can see all of those cables laying down, and you can kind of understand what's going on in this particular block. So I'm going back, showing my trackers. However, what's important here, that in our hierarchy, again, if I select this particular block and we'll dive in it, you will see that inverter connects to transformer, and then there are a bunch of different combiner box circuits or combiner groups like this one. So for example, I can just go to this combiner box and I can actually see, if I isolate this group, you can see how those trackers actually connected to inverters. So you can see that they have like extenders, then trunk bus, and then the DC feeder goes and connects it to inverter. So another level of details, right? So another layer of complexity. And so with those combiner boxes groups, we can actually go and see how much information we need from there in order to think about layout in a way, let's say, to make it like buildable, right? So I will search for, let's say, average voltage drop, and will colorize my combiner groups by average voltage drop for this particular block only. So I can see, for example, the most, you know, like the combiner groups which has the highest voltage drop. So I can basically go and actually check on this one. Okay, this is actually this one. And so we can even speculate a bit, why is that this one has a maximum voltage drop? And the reason is like the furthest from inverter. So the DC cable runs through this whole kind of distance, and that's why we get this. But now let's have fun. So let's go to the whole layout, right? So I'll hide my terrain. You can see that this block is colorized, but now what if we're gonna go and like find the worst combiner circuit for the whole layout? So we'll colorize the whole layout, and we can see the 1, 3, 8, 5, 3, 9 percentages, which might be unacceptable for us. right? And we can like go right there and we can select this one and we can quickly isolate this one. And we can actually see that that was pretty ugly block. And so we needed to run this DC cable all the way, right? So if I'll show you this particular block in here, let me just show annotations, block number 3, 2, right? So we didn't like spend time designing it properly, but you can see that this is a block quite kind of disconnected, like many arrays. So that's kind of another level of complexity, right? And so then we can go further and further all the way to trackers, and I will show you real quickly like a little bit about trackers and strings. Let's just colorize it back to see our blocks. So then the terrain is hidden, and I'm going real closer to my layout, where you can see again lots of details, trenches, trackers, wiring, all of that stuff. So the thing is that each tracker, you see, this is kind of terrain following tracker. It has like lots of information. First of all, it configured really well, right? So it has a bunch of different configurations, piles configurations, and you can see exterior, interior, edge, like different like pile positions. And this tracker knows how much energy each string from it produces, right? Another layer of complexity. Well, this actually allows to find the best and the worst performing blocks. So, and then, as well as like each tracker knows like shading factors, percent angle. So you know how much energy you're losing on those strings. And so you take into account terrain kind of, and you calculate the energy production so you can find the weak spots. And so as you can see, like so many level of details, and we'll probably show you the latest one. Let's have a bit of a fun, and let's try to find on this particular project all the trackers with the slope above 10%, and we want it to be north facing. Okay, so let's do this. We're gonna do a search because we have this kind of BIM modeling software, PVFARM. We can do a fancy search, and what it means is that we can choose a tracker, and then basically, let's say I will search for the slope. I'll actually search simply for first to last pile because it's terrain following. So then I'm going to select a range of trackers, let's say 10 above 10.4 percentages, and then I will add a end filter, and then we will search for facing, and then we will just click on this north and we'll select those trackers. So now I can turn off this filter. So that's exactly how we can kind of find those trackers which we can work about. So again, I will stop sharing right now and we'll go back to my presentation. So yeah, so basically, again, what I showed in the previous 3 slides, more like a kind of in action how PVFARM combines those layers together and how we think about layout in terms of complexity and hidden, and basically all those hidden considerations. And this is exactly what it is, right? So it's not that simple. So now we're gonna go and we're gonna talk a little bit about layout features, kind of key features, and we're gonna break down the building blocks of layout in a way. We won't be focused on electrical or civil part, or maybe like a structural part, because we had a previous webinars about it. So now we're gonna be focused purely about kind of layout and what kind of features are available there. So this is a first chart. This is a chart for hipsters, and this is old school. So probably stick to old school because old school is a good one. So we have again different groups of layout features. Like for example, let's start with arrays. We have a tracker mix. It might be single tracker, multiple track layout. Tracker shift, it might be shifted, non-shifted, and etc. Right? So there might be different blocking strategy. No blocking, hard ILR, meaning that we have a very strict ILR. And then we have a different block partitioning. Can our blocks go through the boundaries? Are they encapsulated? Like, do we have a rods as a placeholders, or do we like design a rods connectivity and provide a meaningful rods? So we will talk about those on a bunch of examples, and let's go basically. So first one, arrays alignment. And basically, a bunch of next slides, we will be talking a lot about like picture from the left, picture from the right, and what's actually happening. So you can see here on the left one, trackers went aligned. That's why the algorithm maximized for DC, and that's why you see those kind of curvature trackers in here and in here as well. While on the right picture, those are pretty nice and clean here and basically here as well. So as you can see, as a result of this transition, we basically lost 0.6 megawatts DC, but we might be beneficial in terms of construction and buildability standpoint, right? Let's go to the next one. So tracker shift, it's a fancy one. Sometimes there are boundaries where you can actually shift your trackers and you can fit more. And obviously we use trackers because mostly we presented trackers here, but it can be done the same story for the fixed tilt systems. And you can see on the left, non-shifted. So basically all the trackers, they are in line, right? And then on the right, you can see shifted. And on this particular example, we got an extra 2 megawatts DC by simply allowing the algorithm to shift trackers within the boundaries. Okay, so tracker mix, that's the probably easiest one. On the left, we used one particular tracker, and on the right, we used 4 different types of trackers. So usually on the real project, mostly like, especially if it's a nested architecture, people use 2 types of trackers. Sometimes people use 3 types of trackers, I mean by lengths, right? And as you can see here, on the left one, we got basically like a 6 megawatts DC less than on the right one by simply using a bunch of different tracker lengths and and having fun with the shifting capabilities. So blocking strategy. So again, left one, none, right? 19.3 megawatts DC. Right one, 89.8 megawatt DC. So when we start doing blocking based on our ILR or DCAC ratio, we might start losing tables or trackers simply because we have something from the left and we want to block it out in the most efficient way, and we want to lose as least as possible, right? If it's a hard ILR, a hard DCAC ratio. And this is more like let's say we will have more slides. I'll explain more about this, but basically, essentially, that's the another place where the important to evaluate trade-offs. So the next example, block partitioning. This is a fun one. So basically on the left picture, we run layout for this bit, and then for this bit, basically we didn't allow it to mix blocks. So, and then for the right one, we allowed it to mix blocks. However, on the left one, as you can see, the shift was happening again independently for each parcel. But on the right one, because we kind of connected those parcels, so there were a total kind of global shift for the whole site. So this is why we lost DC here, actually. But sometimes it might be extremely beneficial to actually, especially right now, we know that projects getting uglier and uglier, and sometimes you just have no way of not letting blocks to share boundaries, and it's just good to have this option. And just another example for you guys. So next one is about layout architecture. You can see roadside architecture, which is essentially when your trackers, they are on the same line, and then you have a skid roadside, right? And then you have a notch or nest in here. This is where you kind of you make a less glass to glass because of the nest. You also kind of use a shorter trackers there. And then the bigger your site, the more benefits you can get from a nested architecture. But it also depends on, site complexity. Because if you have like lots of small kind of site islands, then you wouldn't, you probably wouldn't get the enough benefits. But again, on this particular one, we got 1.3 megawatts more by simply shifting towards a nested architecture. So, that's quite, I would say, popular request within the industry, central versus string inverter. And again, in this particular case, we simply considered the equipment cost and labor cost, installation cost. We didn't take into account life cycle optimization. That's why I think we got pretty close results, just a 300K difference. However, usually on this, when people make a decision about central versus string, they actually worry more about kind of operations and maintenance. And this is, again, another additional layer which you add on top of what you have, and then you actually make informative decision about it. But still, it's nice to run both and to see which one works best. And typically, string inverters might work better for crazier boundaries, because you can actually have like inverter groups isolated and connected together, and rather than with central one. But again, there is no like a one rule that will work for any boundary. That's why it's important to run both simulations and see what's going on. Let's jump to the next one, rods. Again, this is kind of, we call it placeholders, because we design like a minimally required rods quickly, just so people can actually kind of evaluate what works better. And usually rods direction in combination with the blocks footprint and in combination with electrical architecture, it needs to be considered together, because in that sense, you can actually see the benefits of using, for example, north-south rods for the trunk bus solutions, and then east-west rods and very kind of north-south stretched blocks for the harness combiner solutions. That's why we kind of made those like rods as a placeholders, where you can actually make like a quick tests and see what's going on. So in this particular case, 0.4 megawatts DC, which is less than 0.5%, not significant. But there is another layer to it, which is electrical considerations, and electrical cost might be very much different for this particular example. So now we're gonna discuss block aspect ratio. You can see on the left one, the DC was maximized, basically. And that's why we got the blocks that are, people demand those rectangular blocks, but sometimes they also demand max DC. And so on the left option, we actually produced less rectangular blocks, but more DC, while on the right option, we lost 1 megawatt DC, which is more than 1% of this particular DC capacity for this project. However, the blocks are much more rectangular in a way, and this is a good example of kind of trade-off people need to consider when designing layouts. So again, in terms of rods, this is more like about blocks. You can see you can have a blocks like kind of stretch in the east-west direction, or blocks in the north-south direction. And again, usually it's being defined by electrical pattern or electrical architecture or DC collection system that's been used on this particular case. However, sometimes, again, especially when you work in a tight boundaries, and let's say you want to have an efficient blocks in terms of DC-AC ratio, you might end up in a situation where like a different block configuration will just produce more capacity, more energy on this particular side. That's why, again, worth considering both options and see which one works the best, and especially in combination with electrical considerations. Okay, next one, inverter mix. Very popular use case, especially when you, like on the left one, we used one inverter. So on the right one, we used like a smaller one. I don't remember exactly what, I think it was SunGrow 3600 on the left, and then we mixed it with SMA 2500 on the right. And so as a result, because we had a smaller block, so opportunity to use more trackers, we actually got 2.7 megawatt DC more on the right. And this basically happened because we could use those areas that I'm drawing on the left, simply because we had a smaller blocks and we kind of could allocate them more efficiently. Okay, so that's basically a bunch of examples where we try to show layout features, different layout features, and try to kind of visually explain what those mean. Now we're gonna go and we're gonna talk about how layouts evolve. And typically layouts they evolve naturally, right? So guided by available data and decision-making at each stage. So if you don't have a, accurate terrain model at the beginning, so you will make decisions based on assumptions, so you don't have this data. But as you will get this data, you will start making more informative decisions. And sometimes it's just about quality of your assumptions when you don't have data rather than the accuracy when you have data. So it's a fun one. So let's, this is kind of our scheme on how layout evolves. It's custom. You know, we have this kind of formal scheme where like request for proposal, pursued, design 10%, 30%, 60%, 90%, IFC, construction. That's a good one. But we just wanted to think about it from layout perspective. So from a layout perspective, there are 7 steps. So first one, goal setting and requirements gathering. Second one, context and restrictions analysis. So the third one, exploration, meaning the finding a feasible solution or direction. So when you don't know yet what equipment you're going to use, you just basically considering, or developer considering this as an investment. It's quite important to understand, okay, can I make something here which will bring me the money from my Excel spreadsheet, right? So that's where exploration happens, and then the phase of equipment selection, and then the phase of optimization. Optimization phase is a fun one. This is where the couple of roles start working together. Civil engineers start making stuff, electrical engineers, performance modeling engineers. So this is where people actually balance those trade-offs and try to find the perfect kind of solution. And then design phase, polishing and refining, and then pre-construction phase, ensuring constructability. I think, and obviously when you have the pre-construction phase, you need to stay in sync with your goal settings. So basically your final layout, it should be close to what you've planned, right? So important message here. So I think those stages, they might be slightly different. They might be in a different order. However, there are a couple of things. So there is a time for rapid iterations as well as there is a time for precision. You can see that when you do context analysis or design polishing or pre-construction, this is a perfect phases where precision is super important, right? However, when you do exploration and you just do sweeps and all of this stuff, this is the phase where rapid iteration is important, right? It's not, if you try to be accurate and like try to be worried about roads and all of this stuff on the exploration phase, this is going to be a phase that will take 15 years, right? So this is why here it's about rapid iterations. And then equipment selection is about pivots, being able to pivot if something doesn't work or maybe if something better comes up. So, and then optimization is about trade-offs. I feel like those understanding from a layout perspective are very important because then you know what to focus on, right? So let's go to the next one. We will go quickly and talk about all of those phases. And we're going to bring kind of our perspective. We work with many companies and many people who design layouts, solar PV layouts, and we just, kind of try to summarize all things that we've heard and experienced and try to convert it into some kind of educational material that hopefully will be useful and helpful for you. So goal settings and requirements gathering. The essence of strategy is choosing what not to do, right? We usually say that if you pick one item from each bucket, that's a good description of what you're trying to achieve from this particular project. So let's say if you have an interconnection constraint and then you have a specific capacity target and you want to optimize for LCOE, that's a great goal. So, or if you have a land constraint and you have again, budget limit, and you still want to get highest yield to max capacity, that's also a good goal. So you're basically picking one from each bucket, and that makes the kind of goal setting in a simple way. Obviously, there are plenty of things where it's slightly more complicated, slightly different, but I would say from our experience, this can describe mostly, basically the biggest number of layouts and strategies we saw. So the next, context analysis. So this is simple. I will not spend time here. Sections, parcels, buildable area, solar layout. So I think the one important note here is that people call differently buildable areas. So for us, again, buildable area is something where you can build. Yes, there are very expensive spots, but you can build there, right? If it's your neighbor parcel, you cannot build there. But if it's a I don't know, steep slope, you still can build there. It's just gonna be more expensive, and maybe you will decide to make your trackers work better there, right? But that's kind of in definition, and this is where we can see different people that think differently. But I think buildable arrays, it's a immovable boundaries. Next one is about restrictions analysis. And again, if I go back quickly here, you can see context and restrictions analysis as a second step. So the restriction analysis is simple. Do you have a land constraint or interconnection constraint? If it's a land constraint, then you have, let's say, 500 acres and you just want to squeeze maximum. That's why we use lemon emoji. We want to squeeze maximum DC or maximum yield. And the cost, like dollar per watt, can be extremely high, but it doesn't matter. You want to squeeze maximum. The second option, if you have an interconnection constraint. So you probably have like more land than needed, and you need to choose actually where to chip away. So for example, for this site, you basically chip those areas away because of more expensive grading. And for this one, you chip those areas because of the electrical cost expensive. And as a result, it ended up that electrical cost was more expensive than grading, so you got a better option. That's what we call chipping away strategy, and use X to represent it. And so we make this table with kind of strategies you can pick, and there are some kind of connections that don't work. Like for example, if you have energy target and highest yield, so there is no strategy there. It just doesn't match. Or like if you have a budget limit and you wanna chip away and then you wanna get lowest dollar per watt, it's a dubious one. So basically those, I would say there are 12, based on what we showed, there are 12 like most popular strategies. And then the next phase is exploration, finding a feasible solution. Like mostly currently in industry, people think about sweeping GCR and DC to AC ratio, and then you get a lot of sweeps. But there are some other considerations to it, which is different systems, single axis tracking system plus fixed tilt system, combination of those systems, different layout architectures, nested plus roadside architecture, different like roads orientation. So basically, we tend to think about this, that there are plenty other things on top of GCR and DCIC ratio, which might be very important, especially if there are some knowns about electrical wiring. So then the next step is about equipment selection, which is simple, right? You try to align technology with site conditions and cost efficiency and some other aspects. Then optimization or iterating trade-offs phase. This is the phase where, it's kind of multidisciplinary phase where like someone bring layout to the table, and then the electrical engineer says, hey, for your blocks number 8, 9, 10, we're using a harness combiner architecture. And because your rod is at the bottom edge of your blocks, we have a higher voltage drop that client allowed us to have. So can you do something about it? And then, for example, civil engineer, yeah, sure, I'll move this rod here. We'll make this like this. Let's try to see if it works. It's a very simple example, but obviously people, we see like amazing level of complexity, how people evaluate those scenarios. And this is actually the fanciest phase, because so many interactions happening on this actually stage. So the next one, design, polish, and refining. As you get more accurate data, as you get further in the process, you just make your layout better, more accurate, refining, polishing, making nice rods, making, lay down areas, like thinking about construction. So you kind of refining. And then the next phase is pre-constructions, where you actually ensure constructability, thinking about piles. You want to have 20 types of piles, not 120. You want to have like some sorts, more and more thoughts about what you can deliver, how you can build it, and etc. Right? So basically 7 phases. And before we actually start talking about the next, before we actually start talking about quick and dirty versus built to last, finally, it is important for us to talk about such a crucial concept like a good enough layout. Like there is no kind of perfection. People need right decisions at the right time. So what does it mean having a good enough layout today? And good enough layout is a great concept. Usually when the greatest engineers we work with, they use this term quite often because they do understand that there is no perfect solution, and it's more about, okay, what do we have today? So guys, which one is good enough? So we have 3 layouts, same boundaries. We can start from the left one. The 81.1 megawatts DC, 17 blocks. ILR or DCAC ratio varies from 124 to 136. So, right, great. So maybe a good solution, but what if I want my inverters to be more efficient? I'm gonna stick to 132 ILR. It's just an example. Usually people, they have a range, but then I will lose 1 block. I'll have 16 blocks and 76.2 megawatt DC. And then what if I want to optimize for electrical wiring and I want to see exact same blocks, perfect rectangles? So in that particular case, we're going to fit only 11 blocks with the same ILR and we will get 52.3 megawatts DC. So you see, it's a negotiation between competing priorities. And basically everyone chooses what's important at this particular stage. Maybe if the goal for this parcel was to generate 50 megawatts DC, this solution might be the best. Right? If the goal was to provide 80 megawatts DC, this one will be the best. So hard to say which one is good enough without context. So next one is about contradictions. Layout needs to be consistent unless we need more DC capacity. We aim for rectangular unified blocks unless the site constraints force adjustments. Blocks should remain compact unless grading makes it too costly. Right? So there are plenty of contradictions, but as great design is about embracing contradictions. So next one is about good enough is a snapshot in time. Check it out. So the first one, we got lots of, look at this. This is a very ugly rods. We got 75.3 megawatt DC. And then we designed rods better, like we made an entry here. So we got a little bit more DC, right? 2 megawatts more DC, which is substantial. And then we also designed roads differently, but also well connected. So when I say well connected, that means that the track can go all the way here, turn it here, go back, go here, turn it here, go back. Like on the left one, you can see that it's just connected everywhere. So could we say that the left one is a good enough? That's an important question, and I think it depends where you are in the process. Let me jump to the next slide. Now this one. You see on the left one, we didn't use those kind of north-south roads. We just used east-west minimum. We got like more DC. And then as we designed meaningful roads, we started to get less DC. Right? 2 kind of different but the same situations. You can see that the left one, in the first case, it was designed, kind of conservatively. In the second case, it was designed kind of freely, like less roads. But in the first case, whoever did this actually leaves some room for the future. So when I'm going to the next version here, I'm not losing DC. I have a room to design rods well, but at the same time, I'm good. So I have a room. And on the second option, I don't have a room. I start losing DC when I'm designing roads well. Meaning that among those 2 cases, this actually is good enough, especially if it's done like first client meeting and maybe the first time we saw those boundaries, because this layout is a step toward a better layout tomorrow. You kind of manage the risk. You kind of knew that you will need to have a better attention to roads. So that's one is good enough. So that's a tricky one, but just wanted to talk about it. So basically, takeaway about good enough is not one answer. It depends on project goals, what matter most, balancing trade-offs, not perfection. It's a moving target. So it shifts with new data, new constraints, new optimization goals, right? So now let's go to the next one and let's talk about quick and dirty versus built to last. And this is an important topic. It is more about, I'll go to the next one. Quick and dirty doesn't mean bad. And built to last doesn't mean good. We want it to mean good. The thing is that it's basically what we wanted to emphasize is that those concepts are just, they are kind of defined in time, right? When you have goal setting, context restrictions, exploration, equipment selection, you kind of like, sometimes you need to run quick and dirty. You need to quickly generate something, you need to get some results, you need to make decisions. And you don't have data to make the right decisions, so you will make decisions based on assumptions, right? So the more you know from the construction, and the more experience you have, you can actually make that good assumptions, like with those rod example, right? We knew that we will need to design rods properly, so we kind of left some room for that. Same here, and there are plenty of examples where people can make a very good quick and dirty layouts. And so quick and dirty, making quick and dirty good enough is about assumptions and risk management, right? While build to last, making build to last good enough is about polishing and ensuring buildability and life cycle optimization. This is basically two concepts which kind of show the timely importance, how the importance of things shift, you know, as you go through the layout evolution stages. So, and that's why both, they need to get lots of like insights and experience from the construction O&M, but it's just important to know that here roads are not important. Here they are important. And it helps to actually kind of decide what you're going to spend time on when you have a limited time here and there. So now let's talk about ways to design layout. That was the kind of explanation of what's quick and dirty versus built to last. Before we talk about ways to design layout, and we will represent a bunch of kind of design workflows, I just want to explain first layout hierarchy. Electrical hierarchy, tree and table group, which is trackers of fixed steel, then combiner group, blow, medium voltage group layout. So people design layouts differently. So there are different orders. For example, fitting layout with tables, grouping tables into blocks, and then splitting blocks into combiner groups. One order. There are some people fit layout with pre-made combiner groups, and then they combine groups into blocks. Another way. And we also saw people who actually fit layout with pre-made blocks. So it's kind of different strategy. Second one optimized for electrical wiring, for example. The third one optimized for great DCAC ratio, great efficiency of inverters, but you might have like less balanced combiner groups. So it's like each has its own pros and cons. We tried in the past the fitting layout with pre-made blocks. After a couple of iterations, that database of blocks, it wasn't maintainable. So because like every new layout, every new tracker, every new like simple thing creates additional like 100 of blocks. That's why it was extremely difficult to manage, and they become obsolete quite quickly. So it was difficult to make it. However, like there are some manufacturers who can afford like building like a fully pre-made, prefabricated things. Those might work well with this strategy, right? So then another strategy is about when we start fitting with tables, and then we group in tables into blocks. When we're doing this exercise, we might start losing tables like here, and then here, and then here, especially if our ILR is a hard constraint. And then we split blocks into combiner groups. So in this particular case, we actually, we can use different strategy. We can actually use grouping tables into blocks with soft ILR, meaning that we can actually use all the tables, like you can see here. In this particular layout, we actually used all the tables. And then, again, we got our blocks. So basically, bunch of different strategies, and the way it works is that people work with different strategies based on what they need and what's their goals. And now quickly to the latest, last section of our webinar is about layout design workflows. I have like 2 minutes left before Q&A session. So we actually usually break down all the design workflows in PVFARM into 3 categories. It's advanced automation, it's a fancy expert workflows, and it's a human craftsmanship. So the advanced automation is basically when you configure your parameters, and then you make something. You press a button, and then the algorithms make some layout for you. This is it's a good approach for early stage designs, right? But then because you might get a good enough layout based on what you need, and then you will be moving further. So the next, which is fancy expert workflows, is something already more complicated. On this particular example, what you see here, in initial layout, which is the first step of the GIF from the right, we were having ugly blocks because of the inclusion boundaries they allowed doing this. So then we made a boundary around trackers, and we start kind of cutting them a little bit, and we kind of rerun layout like 10 or 15 times, and then we ended up having like block satisfactory level, and we call it a fancy expert workflow because it requires running advanced automation plus some kind of tricks that you have, like a design tricks. Like every designer, layout designer, they have their own like a tricks working in a Civil 3D or AutoCAD, and basically we kind of that's kind of what we have in PVFARM as well, like a bunch of tricks, many different workflows that helps to actually get results that work for you for this particular stage. So like bunch of other workflows, like expert workflows we have, is about when you choose where to start, rods first versus blocking first. You can start with the rods first. You can get like some placeholders rods, like you can see here, not really meaningful. Then you can come up with something meaningful where things connected, and then you do blocking after this. Or maybe you will start with blocking, like you can see on this particular flow, and then you will, based on your blocking situation, you will make your rods better, simply because you can see blocks and you can kind of see where you need to have a rod, because you don't want your rod to cross your blocks in a fancy way. So that's why this might be, again, we propose both workflows, and for some boundaries, rods first work well, for others, blocking first works better. So chipping away, I mentioned this term already. That's when people have more space than necessary. And so essentially the workflow we support to make a good enough layout is that you have 590 megawatt DC, let's say, and you want to have 500. So what you do clustering. So you basically break down your layout into areas. Then for each area, you run kind of optimization. So you try to find the best configuration, and you make an analysis like cost per watt DC or LCOE cost. And then after that, you basically kind of grade those clusters based on how expensive they are. And then you basically choose which one to throw away and which one to leave. And that's how you end up with your target, while not using the most expensive areas, for example. And the most expensive areas, they might be civil or electrical ones. And then now we have the third way, which is human craftsmanship. This is the area where you do like so many things manually, and essentially like moving trackers, regrouping combiners, regrouping blocks, or like removing certain trackers. So it's kind of something that always required, especially later in the process, when you want to have a layout cleaned out, like make it acceptable, make it good enough for a later stage. And that's also something we do support. This is why we actually break those things down into those three categories. And usually, again, quick and dirty, early stage, advanced automation, then fancy expert workflows somewhere in the middle, and then human craftsmanship. And those, they can actually work together. It's just, again, it depends. As always, it depends. So yeah, that's the topic for today's webinar. So let's, you guys, if you have any questions, let's talk about it now.
Yeah, thank you for the presentation. We're going to get into the Q&A portion of the webinar, so you can submit your questions in the Q&A box on your screen. Our first question is wondering, does the PVFARM software, does it use AI?
Oh, okay. So that's a nice question. It depends what you call AI. We have plenty of optimization algorithms. We have also like fancy mixed integer programming and like lots of robust algorithms. We also do run experiments with large language models and Gen AI. However, we don't have anything in production related to large language models yet. Production meaning available to our customers, because we are fine-tuning it at the moment and trying to make something useful and helpful. Yeah, great question. Thank you.
Gotcha. Okay. Can someone import their CAD layouts and continue working with them in PVFARM?
Yeah, good question. Thank you. Absolutely. So we support DXF import. You just need to put things on the right layers and to make sure that your tables are done correctly. But usually, like for let's say 200 megawatt layout, it takes like 15-20 minutes of preparations. And yeah, you can absolutely import your layout in the PVFARM.
Okay, perfect. Is there a capacity limitation to the software?
Yes. It depends on, let's say, if you stick to layout only without low voltage, medium voltage, and trenches, you can generate up to, I think, 2 gigawatts. If you will want to generate everything, I think our capacity limitation at the moment is around 700 megawatts DC. So yeah, that's the question, but we need to test it on a specific project. We're trying to be, yeah, we try to support as big project as we can. Yeah.
Okay. Awesome. Just looking through all the questions for the best ones. What outputs can PVFARM generate?
So actually, you guys have a link. The project I showed you, demo project, basically, obviously we just made a demo project quickly, like in 20 minutes. So don't search for fancy things there. However, I basically exported all the outputs, which is a PDF report, CSV file with metrics, DXF with piles, DXF with trackers, DXF with low voltage, medium voltage, single line diagram. So basically I exported like 7 files and we send you a link so you can download those and you can check our outputs. Yeah, they are fun.
Okay, perfect. I think this will be our last question. It's kind of specific, but if I want to grade a site north-south or east-west slope to a consistent slope, say maybe 15%, can you do that in PVFARM?
Yes, you can absolutely do it. We also added recently end-to-end vertical exposure, which actually allows you to even consider the difference in between torque tube ends. I would say the process is different from Civil 3D because it takes much less time. So you can make a, let's say, 500 acres project like in a couple of minutes, and you can see results. In Civil 3D, you would need to create a bunch of surfaces, like kind of do a lot of manual work. So that's very different in a way. I would say in terms of grading, we kind of introduce advanced automation for sure. And we support terrain following and rigid trackers and many restrictions. And we also been validating it with real kind of EPC contractors and manufacturers that actually build those projects. So yeah, it's different, but the results are very similar. That's the answer. Great question. Thank you.
Okay, great. Okay, well, that is all the time that we have for questions today. If we didn't get to your question, please, we will reach out to you directly. And afterwards, please take a moment to fill out the survey that will pop up when this webinar concludes. We will use your feedback to improve our future webinar programming. This webinar will be shared with all registrants so you can view it again at your convenience. So I would like to thank our speakers for being here and PVFARM for sponsoring today's webinar. And thank you to everyone for joining us today. Hope to see you at more Solar Power World webinars in the future. Thank you.
Thank you, guys.